Hey everybody, welcome to lesson number 3. And this one is on the ray model of light and plane mirror ray diagrams. For those of you who don't know, plane mirrors are just flat mirrors. So we're going to be looking at how light is reflected off flat mirrors today, and we'll look at some other mirrors in the upcoming lessons. So let's begin with what the ray model of light is. So the ray model of light is a way of representing light as it moves from one object to, of course, your eye or wherever that light ray is actually going. So light is represented by these straight lines that we call rays, which show the direction of light and how it's traveling. Ray diagrams are diagrams that show the path that light actually takes after it leaves its source, and we'll have a look at on how to actually do that in a little bit. So each ray, when we draw them out, will end with an arrow, and that arrow is used to indicate the direction of light travel. So ray diagrams help us describe what actually happens to light when it strikes an object. Now, light, one of three things can happen tonight. It can either be transmitted, and when we're talking about transmission of light, we're talking about light going through something that is completely clear. So when light travels, for example, through a pane of glass, it is transmitted. So transparent material, like glass, absorbs and reflects very little of that light, and you're able to have that light come to you through that surface. Translucent materials allow the transmission of light. So light does come through them, but it's not enough to see through the material clearly. So for example, a frosted window pane that you might have in like a shower, for example, would be a great example of this. So basically light does go through, but it's scattered, and so you don't get a clear image of what's on the other side. And then the last one is what happens to light as it strikes an opaque object. So opaque objects don't allow any light through. Instead of the light reflecting or transmitting there, it is going to be absorbed. And so this is a nifty little diagram that helps figure out what's actually going on. So you have your light source in the middle. On the left, you have a transparent object. So you can see that the ray of light travels from the light source straight through that particular transparent object there, and then of course will travel right through. And so if you are an observer on this side, you can see that light source very easily. On the far right hand side, we have translucent objects. So if you are the observer over here and there is a light ray coming in this direction, when it strikes that surface there, it actually scatters the light. So light goes off in all different directions, and so as the observer over here, where your eyeball is, you can't actually create a picture, an image. So you have that frosted glass feel. And then of course opaque objects, if you're the observer on this side and you're looking just to see what's going on from this source of light, you're not going to be able to see anything. Opaque objects reflect or absorb light. So sometimes they'll just absorb, as you can see from these two rays right here, and then of course this ray here and this ray here represent reflection, so light bouncing off of that object. Of course, you're on the other side, you're not going to get any light from there. So we are interested in seeing how light is going to interact with different surfaces. Namely, we're interested in how reflection actually works, and we'll look at refraction a little later on in the course. That is light traveling through objects there. So the first mirror that we look at is called a plane mirror. So I've given you instructions. Now the instructions are also found on the class website, and you can go on and have a look there. It's the same note here that is there. It'll probably be a little bit easier for you doing it on paper than it will be for me doing it on the computer screen. So without any further ado, let's take a look at the ray diagrams for plane mirrors. So I've given you this set of steps. If you follow the steps, there's no way to get it wrong. So the first step here, it asks us to draw a line to represent the plane mirror. So I'm going to place my my ruler here down on the computer screen, and I'm going to draw a. Ooh, that didn't turn out too well, did it? Okay, I think the ruler is actually interfering with my computer screen because it's a metal ruler. So you guys are going to use a ruler. I'm going to freehand this. So here is my mirror. Now, sometimes when you see these mirrors, they'll have little hash marks like this on the mirror. Those hash marks are to represent that this side, oops, pardon me, this side of the mirror is the reflected side or reflective surface. And then, of course, where the little hash marks are, that is the back of the mirror. So we've done that. We've done line number 1 there. We've drawn our mirror. That line represents my mirror. Now, of course, when you guys do this, you are going to be using a ruler. The second step is to draw a simple object. Now, for all of these ray diagrams that I'm going to be doing in the course, I am going to be using arrows to represent. So I know it says draw a simple object with a pencil. I always draw an arrow. So I'm going to draw my arrow right here. Here is my arrow. Now, of course, use a ruler for drawing the arrow. I've got my arrow like this. Arrows are great because it's easy to distinguish one end of an arrow from another because it's got the point on the end. And then it says label one end of the object point A, so we will do that. This side is point A, and the other end of the object is point B. All right. Now, I want you guys to pretend that gravity doesn't exist. And if you've ever played any sports, whether it's hockey or basketball or baseball or anything like that, or ever thrown a ball against the wall, you'll actually know exactly what it is that I'm talking about here. The next step here is to draw a ray that leaves each point of this object, point A and point B, so that the ray strikes at 90 degrees to the actual mirror itself. So if I was doing this, I would actually, I'm going to draw this on here and I'm going to erase it in just a second. I would place my protractor on the line here. Here's your 90, and I would connect this line here to there. That's exactly what I would do. Okay, so you'd place that there, and that way you know that you're actually at a 90 degree to the actual mirror itself. Just erase these lines here. If the pen is going to cooperate with me, and it usually does. Very good. So before we actually start this, I do want to just mention one thing. When you have to remember that every single point of this arrow, whether it's this point or the point just below or the point just below, there are an infinite number of light rays that are leaving that particular arrow going off in every direction. So the first ray that I want you to draw is going to go from the tip of the arrow here, and it's going to extend perpendicular to the reflected surface. Okay, so I'm going to put a little arrow there to indicate the direction that it's going. Now we know that this is going to strike here at 90 degrees. So this reflective surface, being straight in terms of a straight line, has a special line that you can't see in this ray. I'm going to show it to you on the second ray that we're going to do. But that special line is called the normal line. And the normal line is any imaginary line that comes off of the reflected surface at 90 degrees. So of course, if I was trying to locate the normal line in this particular case, it would be hidden by the actual ray. So it would run right along the same line that the ray is. Now imagine this ray is a ball or a puck or whatever it is from that sports that you play. If I were to toss a ball, and assuming that there's no gravity here, if I were to toss a ball in that direction and it strikes the wall or this reflective surface at 90 degrees, how will that particular ball bounce off? And the answer to that question is, well, it should bounce off 90 degrees. So it should go in, strike the wall, and bounce straight back. Now, if I continue on with my, and that's it. So you're done that particular line. If I continue on with my, rules here, it says draw the reflected ray backwards along the same line as we've already done, and then it says using a dash line, extend that reflected ray behind the mirror. So now you're going to use a dash line, and we are going to extend it behind the mirror in that direction. I'll explain why in just a second. Then I will continue along, and then it says draw another incident ray, so another ray that comes off of point A at any angle. It doesn't matter what angle it actually is at. So here's my next ray. So let's say I draw it off at this angle. Now, in terms of the direction that it's going, we know it's going in this direction. And I said to you guys a little bit earlier that there is an imaginary line that exists right off of the reflected surface that is at 90 degrees. This we call the normal line. And the normal line is always 90 degrees to the reflective surface. So it's 90 degrees here. Just erase that. Now, why do we draw this normal line? Well, we draw the normal line because the normal line is where we take all of our measurements from. So again, I asked you guys to have a protractor here. If I had a protractor, it would look something like this. This would line up, this part here would line up with 90. And so you're able to make a measurement between this point and this point. Okay. Let me just erase this, and I'll help you out here. Oops. So this angle here is called our incident angle. Now we use a special symbol in physics here to represent that. We use a symbol called the theta. It's a Greek letter. And because this is the angle of incidence, we use a little subscript I to represent the angle of incidence there. Now, for those of you who played sports, I just erased it. Let's come back. For those of you who played sports, you will remember that oftentimes you may have had to do a bank shot or pass the puck off the boards if you played hockey, or do a chest pass that bounces off the ground if you're playing basketball. Now I want you guys to imagine that this ray was a ball again. Now if I tossed a ball at some angle off of this surface, you'll realize very quickly that that ball will hit, and when it bounces off, that wasn't a great picture, great line there. When it bounces off, it's going to bounce off at an angle that is equal to the angle that it came in at. So in other words, this theta and the other theta are equal to one another. Theta I is for our incident ray. This ray here is our reflected ray, so we're going to call it theta little r. Okay, so if we go back to our rules here, it says that rule number 7 was draw another incident ray from A at any angle. And then it says draw a normal line, as we've done there. The normal line is located at 90 degrees to the mirror. And it says measure the angle of incidence and draw the reflected ray. So you're measuring off of the 90 towards that ray. And then, of course, on the other side, you'll do the exact same thing, but it'll be the equal but opposite angle. Now, the nice part about your protractors is that you have two lines, or two sets of numbers. One starts from 0 on the left and goes to 180 on the right side of the protractor, and then the other line starts 0 on the right, goes to 180 on the left. So making these measurements is really, really, really easy. Now, the last part that we're going to get at is taking the reflected ray that we've just drawn, so this one right here, and reflecting or drawing a dashed line backwards into the mirror. Now, of course, this will work out a lot better for you because you're going to be using a ruler. But anyways, I'm freehanding it. Now, the real question is, why did we do that? So in order to answer that question, we have to ask ourselves, well, how is it possible that we are able to see something, whether it's a reflection or if you're looking at something or whatnot? Well, it turns out that in order for you to see something, you have to have light rays that come together at the back of your eye, they converge at the back of your eye, and that will allow you to focus an image. So when we're looking at a mirror, a reflection, we are really seeing the reflected rays. So you've drawn 2 reflected rays so far. Your first reflected ray was in the first line, and it's going off into infinity in that direction. And the second reflected ray is going off into infinity in that direction. Now the question is, will these 2 rays ever meet together? And the answer to that is no, they won't meet together. And so our brain is actually quite an amazing organ. It is able to extrapolate where those light rays would have come from. And so in other words, I'm able to extend it behind the mirror for both of those reflected rays And where those rays cross, so this point right here, that represents point A in my reflection. Now, we're going to follow the same process again, and we are going to do this for point B. So, of course, with point B, you're going to take your ray, it's going to go in this direction, it's going to bounce back in that direction, and we are going to extend it through the mirror there. And then we can pick any other angle, again from point B. Maybe we'll come down at this angle, and we know that there's a normal line here, and you guys are just repeating what you've done. We have a theta I here, and that means that it's going to bounce off at some angle that we know of roughly the same, exactly the same if you're using a protractor, that angle, and then this is able to extend backwards into the mirror. You want to do a solid line, you want to do a dashed line here. And where that crosses, that represents point B in the diagram. Now, if point A is up at the top and point B is down here, we can recreate this particular arrow as a reflection. Forgive my terrible drawing. And the pen that doesn't ever want to work properly. So there you go. You have recreated your drawing. So this is your reflection over here. Now, we have to have a way to identify different features of these reflections. And so we use a special acronym called LOST. So it's down here. Now, usually I don't write out what the L, O, S, and T are. I just write L, O, S, and T, but I've written them out for this in this particular case. This is the first time you're learning about it. So we are going to try and describe the image relative to the object. So the L in LOST stands for location. So you've got a couple options here in terms of the descriptive words. You can have it either closer to the mirror, farther from the mirror, or the same distance. So in terms of this particular diagram, my reflection is the same in terms of its location relative to the mirror. So you're comparing the image's location, so that this is the image, this here is the object, and you are comparing the image's location to the object's location relative to the mirror. So this distance right here, and I'll erase that line in just a second, but that distance there is the exact same as this distance here, if you've done this properly with the ruler and everything. So we have the same location. The second one is orientation. So orientation can get a little bit confusing. You remember you have to compare the image to the object. So you have two options for descriptive words. The image can either be an upright image, or it can be an inverted image. And remember, you're going to make the comparison between the image to the object. So in this particular case, the arrowheads are still both pointing upwards. And so we have a situation where we have an upright image. Okay, we have an upright image. The next one, in terms of our descriptive words here, is the size. So you can imagine what we have here. We either have, in terms of descriptive words, we either have larger, smaller, or the same. So the question is my object larger, or sorry, is my image larger, smaller, or the same size as my object? And the answer in this particular case is it's the same size. When we do some of the other mirrors, you'll see how these change and manipulate. And then the last one's the most difficult to understand. The last one is the type of image. Now we have two types of image. You can either have a real image, or you can have a virtual image. Okay, so I'll tell you the cheating way to do it, and then I'll tell you what it actually means. So if the image appears on the same side of the mirror as the object. So let's say the image appeared over here on the left side, which is on the same side as the object, then you would have a real image. If it appears behind the mirror, you have a virtual image. That's the cheating way. What do we really mean by these things? Well, the question is, do the light rays that converge actually exist? And the answer in this particular case is no. The light rays behind the mirror, where these dashed lines are, these light rays don't actually exist behind the mirror. We've drawn them there, and our brain is able to extrapolate that and actually figure that out. But those light rays don't exist. Of course, the light ray hits the mirror and bounces in the opposite direction. So in this particular case, we have a virtual image. Now you'll see as we go on and do the other mirrors, how you might have a real image. Now you should also know, and I'm not particular in terms of how you do this, there is another acronym that does oftentimes come up, and that is SALT. So SALT stands for size, attitude, location, and type. Really the only difference is the A and the O. I personally like the O because orientation means, is it, upright or flipped over. Attitude means that, so is it upright or is it inverted? I don't use this, but a lot of teachers do, and I think the textbook that we have in our class also does use this particular acronym. I use LOST. I think it just works better for me. So that's how you would do your ray diagrams for plane mirrors. So you pick 2 points, and you have 4 lines, 2 that run perpendicular to the reflective surface, and then 2 that run at any arrow. Draw out your rays, take your reflected rays, extend them behind the mirror, and then of course you'll connect them on the other side, and you'll do this. Now, when we look at an object in a mirror, there aren't 1 or 2 rays. There are an infinite number of rays that are going off in every possible direction. If I was standing in front of a mirror and I was looking at, let's say, I don't know, somebody right next to me in the mirror, if I'm looking at their reflection, whether I'm standing to the left of them or to the right of them, or 5 feet back or 5 feet forward, or up on top of the counter maybe, or whatever it is, it doesn't matter where I'm standing. I'm still able to see them in the reflection of the mirror, and that's because there are an infinite number of rays. So of course, the more of this step or these steps that you follow, the more accurate your image is going to be. In the practice, and you guys will have already opened up the sheet, you'll find that one of them is a pentagon. And so in a pentagon, if you do this whole process with each one of these, so one going in that direction, one going in that direction, one going in that direction, one going in this direction, going in that direction, you'll notice that the more of these you do, the more accurate your image will become. Okay, so the more points of reference you have, the more accurate it becomes. So with the pentagon, I would choose 5 points, and I would do it 5 times, and then I would know exactly where those points are in the image behind us, or in front of the mirror, I should say. In any case, if you guys have any questions with this, please email me. The instructions are pretty straightforward. And yeah, good luck, and I'll see you in the next lesson. Thanks.